1.1 starts a fun chapter. We're going to start out with sequences, and that's going to transition into series. Sequences are just kind of what you might imagine. It's a list of numbers. Sometimes there's an order to it, sometimes there's not, like the digits of pi or the digits of e or square root of 2, those kind of things. But this is a sequence. This one in particular happens to be an arithmetic sequence. A lot of times what we do is we refer to this sequence by a letter, but then we subscript things to refer to each individual element in that sequence. So for instance, I could call this a sub 1, and that'd be a sub 2, a sub 3, and so on. And by doing that, sometimes we can come up with a general formula for this sequence. In this case, because it's an arithmetic sequence, I can find one pretty easily. Then remember this from their college algebra. A sub n would equal the first term plus n minus 1 times, well, what is it that we're doing to get from one term to the next? You're adding 3. So it's n minus 1 times 3. You could simplify that. I prefer it like this. The next one's pretty cool. That's called the Fibonacci sequence. Has anyone heard of that before? Fibonacci? Big thumbs up from Kaiser and a few other people. Good deal. So to get one of these, you're going to add the previous 2. So 1 and 1 gives you 2. 2 and 3 gives you 5. So there's a little typo there. 5 and 8 give you 13, and so on. So that's the Fibonacci sequence. There is a version of this for the Fibonacci sequence. It's just kind of a pain. It involves the golden ratio, amongst other things. The last one's kind of my favorite, and I'll apologize to Jeff Parent veterans in this class who've seen this before. This is the factorial. So this would be, for instance, that's 3 factorial. So let's call this sequence C, C sub 1, C sub 2, C sub 3, etc. To get these terms, C sub n, you're just going to do n factorial. So this would be 5 factorial, for instance. You could write that as 5 like that. So in a math class, this is 5 factorial. What would this be in an English class?
5.
5. Yeah, there you go. Thank you. All right. Well done. So there's the notation that we're going to be using. Now, sometimes you'll have an explicit sequence, in which case you can just plug in the value of n and get the subsequent terms. So if I wanted the first 4 terms and then the 100th term, I can do that pretty easily. So to do that directly, you're just going to sub in the first 4 terms. A sub 1 would be 4 times 1 minus 4. That's going to be 0. A sub 2 is going to be 4. A sub 3 is going to be 8. A sub 4 is going to be 12. But how about A sub 100? What's A sub 100 going to equal? Who's got my back on that? Come on. There you go, 396. Now you can make your calculator do these kinds of things in a couple different ways. Let's take out our calculators and take a look at those. There's nothing wrong with just putting it in the y equals key and making it do there. Nothing wrong with that at all. But if we change our mode in our calculator, then we can get it to do a little bit more than what we did with just a regular function there. So let's change our mode. If you notice, there's 4 letters across here, x, t, theta, and n. We want that n there, and you're going to get that from the sequential mode. So go down to the line that says function, cursor to the right that says sequential. When you've got that setting there, then you can exit out. I always hit the second key, then the mode key. I think you might also be able to exit out with the clear key, just not my style. Let me clear those up. When you go back into the equation editor, it looks a lot different. That's okay. Let's actually type in the sequence, or the formula for the sequence, I should say. That's going to be 4n. Notice that when you hit this key that you're used to getting an x out of, now it gives you an n. 4n minus 4. We don't have to worry about a starting value. I'm just going to delete that for good measure. Let's go to the table, and look, you can plug in any value that you want and get the subsequent values for the term in your sequence. So let me just delete these, start all over. 1, 2, 3, 4, and I don't know, 100. Looking pretty good. Now, being able to choose your own value of n relies on the assumption that you have your table set up correct. So, quick look at that, second, and then the window key. Your table setup settings should be like this, and like I've said often enough, leave it here the rest of your life. All right. Nice, nice. Let's move on down to a different example, and this is why we needed to change the mode in our calculator so we could be able to do stuff like this. This is called a recursively defined sequence. It's kind of like what we had going on up here in Fibonacci. So, for instance, to get, say, the fourth term in the Fibonacci sequence, b sub 4, what am I doing? I'm adding up b sub 3 and b sub 2. So it'll be b sub 3 plus b sub 2. Or if I wanted to get, say, the fifth term, b sub 5, that'd be b sub 4 plus b sub 3. Can we generalize that? What's this going to look like in general when I look at, whatever term, the nth term in the Fibonacci sequence? B sub n. Well, to parse that out, start looking at these things here. And take a look at the relationship between this variable or this number and this one. How does this number compare to the subscript that I have here? It's 1 less. Yeah, so n minus 1. So b sub n minus 1. How does this one compare to this, or this one compare to this? Minus 2. So this is a recursively defined sequence. You can't easily jump up to, say, b sub 100 for the Fibonacci sequence. B sub 100 would mean you'd have to have b sub 98 and b sub 99. To get b sub 98 and 99, then you'd have to have previous terms. So it kind of, becomes a real nested mess. Now, there are a lot of programming languages that work with recursive programming, and it can be very powerful. It can also be kind of crazy and complex. But fortunately for us, we don't have to work there. This is a recursively defined sequence. To get a sub n, I need to know what came before it. I can't just fill in a number. Now they have to give you something with which to start. So that's going to be your a sub 1. They tell you that a sub 1 in this case is 4. Let's do this one by hand first. So if I want a sub 2, that's going to be 2 times a sub, 2 minus 1. And let's put that in there like this. But 2 minus 1, I'm trusting you can do that one without your calculators. That's 2 times a sub 1 plus 3. What was a sub 1? A sub 1 they gave us, right? That was just 4. So 2 times 4 plus 3 gives you 14. Nice. Now that I have a sub 2, I can get the next one. But a sub 3 relies on a sub 2. So let's see if we can't figure that one out. A sub 3 is going to be 2 times a sub 2 plus 3. It'd be a sub 3 minus 1, which is a sub 2. But we know what a sub 2 is, right? What's a sub 2? 14. So, okay. 14 plus 3 times 2 is going to give me 34. And so on. You keep on going. I'm thinking the next one's going to be 74, but do you see the pattern in what you would have to do? What would we have to do to get a sub 4? A sub 4 would be 2 times what?
34 plus 3.
Yeah, 34, which is a sub 3, plus the 3 there. Let's see if we can't get our calculators to do this. So I'm trusting that you have it in sequence mode because this is not going to work with function mode. Let's go back up here to the y equals key, and I want to type in this function as close as I can. Now this is saying that this is u of n. All right, the formula for u of n, we're going to have to rewrite the formula for a sub n. It's going to be 2 times u of n minus 1 and then plus 3. So let's see if we can't emulate that. Let me clear this out. 2 parentheses and then a u. Does anyone see any place on this where I can do a u? Yeah. Second and then 7 parentheses n minus 1. Then close parentheses. So you're not going to get the nice subscripts like you see it on our handout. That's okay. Let's add in that 3 and then follow that with a parenthesis. So there's your general term. What's this u sub 1 stuff? Well, u sub 1 is if you have a starting value. It's for your recursive sequences. So what was our u sub 1 in this case? 4. Nice. Everyone got this typed in. Looking good there? Will? All right, thank you. Let me exit out of this. Actually, you know what? I'm not even going to exit out. I'm just going to go directly to the table. Second, and then the graph key. And take a look there. There's your first few terms. Look at how big this sucker gets. I accidentally left in 100. Does anyone recognize what that last number there is?
10 to the 30.
Yeah, 6.3 times 10 to the 30th power. It's huge. It's really, really huge. Now, I'm amazed that my calculator could calculate that. Or I guess it's a computer here. Because it has to calculate all the values before it, too. Your calculator might be a little slower in rendering that. I don't know. Did that number pop up right away for you guys?
Yeah.
It did? Really? Because my experience with the TI-84 is that their processor is kind of on the slow side, so I'm impressed that it got there that fast. Okay, let's take a look at a different one. Why don't you give yourself a chance to see if you can't find, the first few terms of this sequence. Now, I suggest you try it by hand, just because there's something that, might work out kind of interesting for you with respect to that one. If you're looking at this later, then here's some instructions to put this in and plot this sequence. You can graph those. Notice it's not playing connect the dots here. You're just getting what happens at those integer values of n. You're not getting anything in between.
I set it to sequence, and when I do y equals, it just gives me that. And I tried resetting it, and that's all I get.
Yeah, I think you've got an old operating system on this.
Oh, okay.
It's not, yeah, because right now, the current operating system is 5.8.2. You're at 5.0. So this is kind of long in the tooth. If you update that, you can do the update. Go to.
Because these are one of your calculators.
Oh, is it one of mine?
Yeah.
Oh, okay. I guess here, just take a different one.
Okay. Thank you.
Yeah.
Thank you.
I guess I got to update it then, which is bad news. It shouldn't take you too long to spot a pattern here, right? Maybe like 2 terms to spot a pattern. So a sub 2 is 1 over a sub 1, which is 1/2. Looking good there. Then what? Then we go to, let me make this into a comma. Then a sub 3 is going to be 1 over 1/2, which is back to 2 again. And then what? Then the pattern's going to kind of start repeating, right? I mean, hopefully you didn't keep going after 3. You can kind of see that this pattern is going to repeat itself. If you did take the time to put that into your graphing calculator, you can graph it. So let's see what the graph would look like. So I want 1 divided by u sub n minus 1. So I'm just going to make that a divided by and basically edit my previous command. This time my beginning value is 2. If I go up to the table function, then I see that alternating pattern. Not a big shocker there. Odd numbers are going to be 2. Even numbers are going to be 1/2. So let's do 5, 6, 7, etc. You can get your calculator to graph these things just like we do, polar or parametric equations. So let's set up our window first. What values of n do you want to graph this for? Well, if I'm going to follow along with what I had in the handout, then I'll go from 1 to 10. Plot start at 1, plot step at 1. I won't pretend to exactly understand what those things are. Now, x min, I'll leave that at 0. X max, I'll put up at 10. Now I'm leaving x min at 0 to kind of correct for a little error that I made here. There's something disconcerting about this graph I just am not really happy about. Does anyone else see something about this graph that, it could be better? Yeah, you can't see the y-axis. Perfect, thank you. Glad to know I'm not alone. All right, so that's why I left x equals 0. As far as the y values are concerned, let's see. I'll go from, let's do -1. It's negative 0.5 really. Just something a little bit less than 0. That way I can see the y-axis and go up to maybe, 2.5. I don't like to cut it exactly right on because then, sometimes you can't really see things. So there you go. There's your points. Even cooler, if you wanted to or needed to. If you're like, well, I need to know the coordinates of those points, hit the trace key and bump around. And it can show you exactly what value. So you don't necessarily have to look at the table. You can just look at a trace of your plot. Nice, nice. All right, some more cheap calculator tricks for you. Let's keep going. Sometimes you're going to be given a sequence and you need to come up with the actual pattern here. So that's what we have going for example H, or in these examples E, F, and G. So that's these, E, F, and G. I kind of gave up yesterday. I was like getting tired of trying to reformat this. I couldn't get that to squeeze onto this other page very easily. So I'm like, you know what? Just go with it. But our goal here is to try and figure out, well, what generates these numbers here. What I would suggest is that you kind of attack the problem in a couple steps. don't try and get the whole thing all at once. So we've got 2, 5 over 4, 8 over 9, 11 over 16, 14 over 25, and so on. We want to come up with, the a sub nth term. Let's write down a few things that we do know. That's a sub 1, that's a sub 2, a sub 3, a sub 4, etc. Does anyone see anything, interesting about parts of these things? You might not always want to look at the first one, because the first one can sometimes be a degenerate case. Things simplify real easily. But can you see anything about this that looks like a pattern? Ethan?
The denominators are perfect squares.
Nice. The denominators are perfect squares. So for instance, I've got 2 squared, 3 squared, 4 squared, 5 squared. So that's a good start. So a sub n is going to have that number squared. So in other words, there's going to be an n squared term in the denominator. So looking good there. The numerators, let's start with the 5. You go with a 5, and then an 8, and then 11, 14. It's looking like there's a pattern here too, right? What pattern? What are you doing to get from one term to the next? Add 3. Let me go back here and remind you of the general pattern for an arithmetic sequence. I gave it to you for this one. In general, it's going to be a sub n equals a sub 1 plus n minus 1 times d. D is that difference between adjacent terms. So in this case, it was 3. In the case of our current problem, it's also 3. A sub 1 is your first term. Let's see if that works for us here. Certainly the 1 squared in the denominator there works. If I regard this as being, say, 2 over 1, or 2 over 1 squared, then my numerators start out with 2, then 5, then 8, 11, etc. So your arithmetic sequence, again, looks like this. A sub 1 plus n minus 1 times d. Can someone fill that in for me for this particular problem? You mean? What would be a sub 1 in this case, or the first term in the numerator?
1.
Maybe 2? We're just looking at the numerators, so 2 over 1. So 2 n minus 1 times, well, what am I adding to get from one term to the next here? 3. So there's your general term for this sequence. Now right now I'm hitting it on all cylinders because I keep on calling these sequences. Later on we're going to start adding up the terms in these sequences, and those sequences are going to become series. I always mix up sequences and series when I'm talking about this stuff, so I don't know, I'll try and be better. But yeah, these numerators represent an arithmetic sequence, and together these terms should trace out this sequence, and they do. You can check it with a few more. You can put in, like, you can check it out with a 5 for the 5th term in the sequence, a sub 5. That'd be 5 squared. That gives us 25 in the denominator. 5 minus 1 is 4 times 3 is 12 plus 2 is 14. It checks. So looking good there. All right, your turn for one, unless there's some comments or thoughts on this. But I hope you see that we didn't try and do the whole thing at once. We did it a piecemeal approach. Let's take a look at example F. Five over 6, 6 over 7, 7 over 8, and so on. So once again, the goal is to come up with the general term for this sequence. Actually, you know what? There's just one there. It helps to label these things so you can kind of see relationships between numerators, denominators, subscripts, that kind of thing. Who's got this one? What are you thinking? Not yet. Okay, let's take a look at this. A sub n has to have two parts, right? It has to have a numerator and denominator. If you look at the denominators here and compare them to the subscripts, 2 becomes 6, or I mean, 1 becomes 6, 2 becomes 7, 3 becomes 8. What is it, what operation is taking you from this number to here, this one to here, consistently? Thanks, Brandon. Adding 5. So you can add 5 to subscript to get the denominator. How about the numerator? What should I do there? Is it just n? Well, no. That'd be a 1 and then a 2, etc. Can I modify that at all? N plus 4. Wow. You know, I got to get a new battery for my old reliable button. It's gone. My that was easy button's gone. So bummed. And I'm afraid that's it. Hannah?
Oh, I have a question. So when finding an equation, do you always find the denominator first, or do you?
No, it doesn't matter. Doesn't matter. I just have been starting there because, like in the last one, Ethan spotted that right away. And it was easy to spot. This one, there's no rhyme or reason for me to start with the denominator. Yeah, you can start with either one. Liz?
How did you find n plus 4?
Doing the same thing we did with the denominator. You look at the subscript. What do you do? You get from 1 to 5, 2 to 6, 3 to 7. You're consistently adding 4. Nice. Now, there is one little layer of complexity I'm going to add onto this. So, let me just call this bonus here. Let's take a look at a sub n as -1 to the nth power. And then look at, you know, n equal 1, n equal 2, n equal 3, n equal 4. That should be good enough. If I put in a 1 here, what am I going to get for a sub 1? Yeah, just -1. All right, so let's do this. So if I put in a 1, I get -1. If I put in a 2, what do I get? 1, 3, -1, 4. Yeah, it doesn't require much thinking anymore, right? What's the general pattern in this sequence? I'm thinking even and odds kind of thing. If it's an odd number in the exponent, then you got a negative number. If it's an even one, you get a positive number. Let's switch things up. Suppose I did b sub n is -1 to the n plus 1. Now what am I going to get? Yeah, thank you. It's basically flipped. Here, when I put in n equal 1, I get -1 squared. That's going to be positive 1. -1 cubed is going to be -1, 1, -1, etc. Okay. One last one here. negative 1 to the n minus 1. Occasionally you'll see this as well. I'll let you work that out for a second for yourself. What's going to happen there? I know. I'll just say, hey, Brandon, what do you think? And I'll get somebody to answer. All right. What do we got here? Brandon. What's something to the 0 power? Anything to the 0 power is 1. And then when I put in n equal 2, I get 2 minus 1. So I get negative 1 to the first power is just negative 1. 1, negative 1. So, wow. What conclusion are you getting from that? Yeah, those two are the same. Doesn't matter if you add 1 or subtract 1 in the exponent, you're going to get the same thing. Now, what you need to keep in mind is that one of them starts negative and one of them starts positive. And you're just going to have to make sure you choose the right one for your sequence's needs. So when we look at this last one, G here, the first thing that I notice is that it starts out negative. So in creating my sequence, what I'll do is I'll start out with that little bit of information. So we got example G, negative 3, 2, negative 4/3, 8/9, negative 16 over 27, and so on. So again, let's see, let's let that be a sub 1, a sub 2, a sub 3. I'm just going to start out by noticing that these alternate. So it has to be negative 1 to some power. Now what power do I want to put here? Do I want to put n or n plus 1? Just n. Because having just n in there is going to start out this series negative. And guess what? Now I'm going to ignore the negative stuff. I'm just not going to worry about it because I've already taken care of the alternating part of the sequence. Now I can focus in on this and this and this. And it might be easiest to look at these numbers, the ones that are already fractions. Let's take a look here. You go from 3 to 9 to 27. What are you doing in each of these denominators to keep on skipping up like that? Multiply by 3. How about in the numerators? 4 to 8, 16. You're multiplying by 2. So it's going to be 2/3 to some power. And this starts with a 3. So this is a geometric series. You might remember those. The general form of a geometric series. Let me call it B sub n equals a sub, not a, but b sub 1 times r to the n minus 1. That's going to be the general form of your geometric series. In a geometric series, you're multiplying to get from one term to the next. You're multiplying by this common ratio. And in this case, you're multiplying by 2/3 to get from one term to the next. Now, there's a couple other varieties of ways you can write this. I still need to put in the exponent here. That's going to be n minus 1. And that's an acceptable form of the answer. Now, you could see this rewritten any number of different ways, but this has got the basic stuff that we need to generate this sequence. Is it conceivable that you might want to check yourself on something like this on an exam? Let's see if we can't get our calculator to check ourselves for us, okay? Now I'm thinking that if we use the horizontal key on our calculator, we can actually get this thing to spit out fractions for us. Let's find out. So we'll hit the y equals key, I'm going to clear out the stuff that's here. And I'll put in the -1 raised to the n. And then I want that multiplied by 3. So times 3 times parentheses. And now I want a fraction. Now it depends on your calculator. Some of you might need to hit the alpha key and then the y equals key to get the fraction. On mine, I get that fraction right there next to the link. So if I hit alpha and then x, it gives me a nice fraction. That's going to be 2/3. I think in putting it in this way, I'll actually get nice fractions when I go to the table. Last but not least, I want to raise this to the n-1 power. n-1 like that. Bam. Are you able to get that emulated on your equation editor? Let's take it up to our table and double check ourselves. Hey, looking pretty good. It's matching all of those numbers. So, pretty happy with that. All right. Comments there on example G. Let's keep going.
Okay, I did have a question.
Yes, please. Go ahead,
Going back
James.
to the paper display.
Yeah.
Where did the 2/3 come from?
So I looked at the fractions and asked myself,
Multiplying by 2.
yeah, you multiply the numerator by 2, multiply the denominator by 3. So to get from one term to the next in the denominator, I'm multiplying each of those denominators by 3. So that put the 3 in the denominator. And likewise, the 2 in the numerator comes from the fact that you go from 4 to 8 to 16. So that's where you get the 2 there.
And where did the 3 out front come from?
That's the first term.
Ah.
How come it's positive and not?
I took care of the negative here with that -1 in the first term. And like I said, and I almost feel guilty, there's probably a lot of different ways I could rewrite this. Yeah, there's a lot of different ways I could rewrite this. For instance, if I split this up into -1 times -1 to the n-1 times 3 times 2/3 to the n-1, and I'm sorry I ran out of room there. But now these things have the same exponent, right? n-1, even though that really looks horrible and I'm embarrassed. So I can bring those two terms together. I could bring these two terms together. So a -3 is what I get there. So I can rewrite this as -3. And then I can also write this as the negative times 2/3, or -2/3 to the n-1. That would give me an equivalent fraction. It's a little cleaner that way, you know, and maybe we could have done it that way had I had confidence that everyone remembered geometric series very well. But, you know, if you don't use this stuff, you forget it. I get it, so I went over it a little bit slower. Could have, maybe.
Thank you.
Yeah, no, appreciate the questions. They're very helpful. All right, let's move on to example H. And some notation here. You're looking for partial sums. The sequence of partial sums is going to be something we're going to be very interested in this course. That sequence of partial sums really relates to this. S1 is just going to be the first term. S2 is going to be the sum of the first two terms. So 2 plus 5 gives me 7. S3 is going to be the sum of the first three terms. So 2 plus 5 plus 7, or excuse me, 2 plus 5 plus 8, I should say. That's going to equal 15, and so on. So you've got a couple more here to find. So if you would be so kind to find S4, S5, and S6, that'd be wonderful. And it's up to you what you want to do to find those. guess I need a couple more terms here. So my next two terms here would be what? 14 and 17. Now, there's nothing wrong if you're doing this 2 plus 5 plus 8 plus 11 plus 26, but there's kind of a shortcut here, right? Because I don't really feel like writing out 2 plus 5 plus 8 plus 11 plus 14. Does anyone know what the shortcut would be? So you could take S4, sum of the first four terms, and then just add the fifth term, right? Plus 14. Doesn't that work? All right, so then you get 40. And likewise, this is going to be S5 plus what? 17. So now we end up with 57. But hopefully some easy points on an exam. If I just say, list the first few terms in terms of the sequence of partial sums, there it is. There it is. Okay, let's try and find the sequence of partial sums for this one. List the first four, and then it says find the nth partial sum. So what they're asking you for is to figure out a formula for this in general after you figure out, what the first four terms are going to look like. Now, if you want to or need to, I might suggest that you actually write out that sequence of partial sums on your calculator and then put it all together with nice common fractions. All right, so let's see who's good with their powers of 3. Hannah, what should I be writing in here for the denominators? Yes. So 3 squared is 9. What's 3 cubed? And the big one, 3 to the 4th. So times that by 3. 81. Yeah, there you go. 81. Powers of 3, aren't you?
Of course.
Yeah. It's okay. Yeah, that's not stuff that you know off the top of your head unless you teach this stuff like I do. All right. So here's your terms. Tell you what, I'll do S sub 1 for you. That's 2/3. Yeah, big help. How about S sub 2? Well, that's 2/3 plus what? Plus 2/9. Now here's where it's helpful to do this on a graphing calculator because a mind is a terrible thing to use. Let's see if we can't do that. So 2 divided by 3 plus 2 divided by 9. And the important thing is not necessarily 2 divided, let's see, I'm missing the 3 there. The important thing is not necessarily the decimal value. The important thing is the fraction. So hit the fraction key and turn that into our fraction. And we get 8/9. Okay. Let's try it again with S sub 3. S sub 3 is going to be 2/3 plus 2/9 plus 2/27. Now the smart thing to do is to take your 8/9 and add 2/27. In fact, I'm going to do it this way. You hit the plus key, it's going to take my 8/9 from this right here, and then I'm going to add in 2/27, and I'm adding it again with this nice horizontal fraction because that'll make the calculator give me back a horizontal fraction. And horizontal fraction is actually kind of interesting. 26/27. Is anyone getting suspicious of a little pattern here yet? We had 3 and a 2, 9 and an 8, 27 and a 26. So S sub 4 is going to be, well, I'm just going to write it as S sub 3 plus 2 over 81. Does anyone want to make a prediction here? What am I going to get for that one? 80 over 81. All right. And it's nice to see that that prediction comes true. So plus, again, added it in as a fraction, 2 over 81. And boy, aren't you smart. Well done. Thank you. 80 over 81. Nice. So that's not where our work ends, though. Our work ends when we find S sub n. What's that general term going to look like? If I didn't want to do this forever, if I just wanted to have a formula, what would that formula be? N minus 1 over n wouldn't quite work. If you put in a 4, n minus 1 would be 3, over n would be 4. So, all right, 3 to the n in the denominator. What in the numerator?
3 to the n minus 1.
Nice. 3 to the n minus 1 in the numerator. That's going to give you those terms. All right? All right, but I appreciate the help and the enthusiasm. So, looking good there. Nice, nice. Comments or questions on example I there? Hopefully this stuff is looking good so far.
I just have a question. For
Yeah, please.
finding n for the 2/3 to the n power, is it just s of 1, you're just multiplying?
Well, I think what you can see here is that there's a little relationship between this and this, between this and this, this and this. This is always some power of 3. For instance, this is 3 cubed, this is 3 to the 4th power, this is 3 squared. So then you can start picking up that, oh, okay, it's 3 to this power, 3 to this power, 3 to this power, etc. So that's where you start generalizing this, is by realizing that these are powers of 3. Yeah, good question. And the numerator, to get the numerator, is just 1 less than the denominator. Thanks for the question. So not long after I started at OCC, I started brewing my own beer. And the peculiar thing that I did with my own beer is that I named them. And I named my first beer after this symbol here. Does anyone know what the Greek letter represented here is? Sigma. So I called it Sigma Pale Ale. Was my first beer. So always a special spot in my heart, coming home on a Friday and realizing, hey, it's ready, and slapping one in the fridge, and it's delicious. In any case, this is some nice notation. If you're familiar with programming, etc., it's kind of like a for loop or a while loop or a do loop in lots of different languages. So we're going to try and find the sum. Now you might see it says find the sum, or I might write expand the sum, etc. But let me write out these first couple here. So you're starting with this index down here at k equal 2. So that sum is going to be 1/2. And then you're going to move up to the next integer and plug that in there. So the next integer is going to be 1/3. And then the last integer is going to be 1/4. And if we put all those together with common denominators, we'll get something. I'm trying to think if it's like 13 over 12. Not sure. Someone want to double check me on that one?
13 over 12.
All right, good deal. 13 over 12. Awesome. And you're done. Yay. Let's take a look at the next one. So for the next one, there's there's all kinds of cool patterns and things that we can do with some of these things, and we'll see a couple of them. I'm going to write this one up here. So at k equal 1, I get 2 to the 0 power. And then at k equal 2, I get 2 to the first, 2 to the second, 2 to the third. Where should I stop? When k equals 5, that's going to be 2 to what power? 2 to the 4th power. All right, so I get all of those, and I'm thinking that that's going to be 2 to the n minus 1 overall. I'm thinking you're going to get 31. So let's see, 16 plus 8 is 24, plus 5 is 29, 30. Did I make a mistake someplace? No, let's see. 24 and 4 is 28, 30, 31. Yeah, 31. Which just happens to be 2 to the 5th power minus 1. Ooh, that's a Mersenne prime. Just talk to you about Marin Mersenne sometime. But the big goal here is just to put in the appropriate values, starting at k equal 1 up to k equal 5, add them all up, and that's your sum. Great. This is a little bonus. We don't need to know that. You're not expected to know that off the top of your head for anything. Let's look at this one. That one's kind of interesting. The interesting thing about this, and the reason I included it, is because I'm not really using the index of summation. Now, the index of summation is these things down here. Typical letters are I, J, and K, but you can use any letter that you want. But notice that the letter is missing here, right? There's no letter. So when you sum this up, the series is kind of on the boring side. The first one, when I equals 3, you get a 5. And then with I equal 4, you get, well, 5 again. I equal 5, I equal 6, and I'm making a mental note that I've got to reduce that index of this summation here. All right, because this is getting kind of boring here, right? Won't lie. 5 again. I equal 8 plus 5 again. That should be a 9. Plus 5 again, I equal 10, plus 5 again, I equal 11, plus 5 again, I equal 12, plus 5 again, I equal 13, plus 5, and plus 5. When you calculate this sum for me on an exam, are you going to sit there and wail away on all your 5s relentlessly? Go 5 plus 5 plus 5 plus 5 plus 5? Probably not. I'm not seeing anyone nod their head like, yeah, that's going to be me. And I'm glad to hear that. So what's the shortcut here?
5 times 11, 5 times 13.
Ooh, I've got a couple different answers. 5 times 11, 5 times 13. Anyone for 5 times 12, right? I mean, let's do them all. Well, if you counted these up, the number of 5s you have, you might be tempted to say, oh, well, it's going to be 15 minus 3. That's 12. But when you count them up, you get a different number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So when you're counting these up to try and figure this out, it's going to be the top number minus the bottom number plus 1. That's how many terms that you're going to have in that summation. So that's the little part that I wanted to get across to us here. So top minus bottom plus 1 equals the number of terms. So for us in this particular case, it would be 15 minus 3 plus 1 In other words, I get 13 times 5, which is 65. So just kind of a little heads up on that one. It could be something that'll help you out here or there. Maybe I'll throw in a problem just to see if you're paying attention to this part. But looking good there. Let's try another one just to give you some practice or the chance to practice. That's going to be example M here. So example M. Sum from k equals 4 to 7. So mercifully, fewer terms than the last one. K times k plus 2. See if you can expand that sum. Try and figure out what the sum actually is. All right, so let's plug in some numbers here. At k equal 4, you're going to get 4 times 6 plus 5 times 7 plus 6 times 8 plus 7 times 9. Are we okay with where we got those numbers? Anika? Prentice? All right. Did someone total this up? Because I haven't done it yet.
It's 170.
170? Awesome. Thank you. Thank you. What would you be asked to be doing if I gave you this sum to figure out? What would that sum be?
Every number 1, 2.
Yeah, it's the sum of the first 100 numbers. So back in Germany, probably in the late 1700s, there was a mathematician by the name of Carl Friedrich Gauss who was sitting in his class, and his teacher got, let's just say, upset at the class and gave him that problem to do, keep him busy. Now, back in Germany at that time, you didn't have paper and pencil like we did now. You had a chalk slate. So you would write your notes on a chalk slate, take them home that day, memorize them, erase it, come back the next day, and start taking notes again. So the teacher gives this problem to the class, and cheeky little Gauss, after a couple minutes, just throws his chalk slate up on the teacher's desk and says, "There it is." And he wrote down one number. Can anyone tell me what that one number would be? It was 5,050. And he was the only one in the class of like 50 students that got it right. And he didn't really write down anything. He just thought about it. Now, I'll show you eventually that there's a formula for this kind of thing. And that formula is n times n plus 1 over 2, where n is this upper limit, assuming you're starting at 1. So we can check it out here. It's 100 times 100 plus 1 over 2. The 2 cancels in there 50 times 101 gives you 50/50. Nice. But little Gauss figured that out on the fly at age 10, which is why Gauss, Newton, and Archimedes are at the top of mathematical achievement. Gauss was a brilliant, brilliant mathematician. In any case, nice little historical aside there for you. Let's keep going. We've got a few more things to tackle in this one. We're going to go backwards. instead of expanding a sum, we're going to write it using that summation notation. So why don't you see what you can do? Let's just choose a common letter here. Let's just choose J equals 1. And I'll let you figure out the rest. Try and write this using sigma notation. Lionel, what should I write here? What should I put in the denominator?
Just be square root of n. What's the denominator? N to the fourth.
All right, denominator. All right. Since I'm using the index of j, I'll write j to the fourth. But yeah, you're free to use a different variable. Good. How about the numerator? Square root of j. And then the summation goes all the way up to what value? N. So that's why I chose to do a different variable, is because I wanted to use n up here. But yeah, looking good. Looking good. Let's move over to this next one. Again, maybe you guys like using n. Let's just try I for a difference. I equals 1 to something, of something. Okay. I equals what to what? Anika, maybe you can help us out. I squared up to 10. Now somebody can kind of race me if they want to. They can add up 1 plus 4 plus 9 plus 16 plus 25, etc. But there's a nice formula for this that people have come up with over the years, and that's this one. So the sum of the first n squared integers should be n times n plus 1 times 2n plus 1 over 6. So James is looking at that, he's really impressed. It's like, wow, that's cool. The good news is you get to memorize this. Not now, but soon enough later in this course. So along with that same formula for the sum of the first n integers, and I'll throw in a bonus for the sum of the first n cubed integers as well. So you got that going for you, which is nice. All right. Yeah, so I think you're going to get, what, 385? Let's see here. That'd be 10 times 11 times 21. So that divided by 6. Just check me out here. Let's see. So that'd be 110 times 21 divided by 6. Yeah, 385. There we go. Equals 385. So nice. It's nice to have those formulas around. The last thing we're going to do is we're going to look and see what happens to these sequences eventually. Do they settle down to something? Do they bounce back and forth? We saw earlier one of our sequences just kind of bounced back and forth. It didn't really settle down to anything. It just kept on jumping up and down between a couple of values. Let me look back at that when we graphed it. Yeah, that was this one here. So graphing it here, 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 etc. But sometimes sequences actually settle down to a particular number. And if that happens, we'd like to know it. We'd like to be able to calculate what that number is. So let's take a look at example n here. And it says, determine whether a sequence converges or diverges. If it converges, find the limit. So this is the limit as n approaches infinity. So this is example. I guess technically this should be example P. So we got a sub n equals 3 plus 7n squared over n plus 2n squared. And the question is, if we start putting in larger and larger values of n, is this going to kind of settle down to something? And you can experiment with it numerically. Nothing wrong with that. Let's take a look at the graph here real quick. So I've got it graphed here. And what we want to consider is what's going to happen to this in the long run. So I'm just going to zoom out the x-axis a little bit. Does this graph look like it kind of settles down to something as you're moving out towards x equal infinity? Or is this graph like taking off? Is it moving towards positive infinity? Marlon, what do you think? Is it settling down or is it taking off? Well, for an example, let's take a look at the graph of y equals 0.5x squared. That graph's taking off. It's getting really, really big, really, really fast. Even if I've made this much smaller, that graph is still getting really, really large as you march out towards x equal infinity. That's in contrast to this graph. Is this graph settling down to something? You don't have to tell me what the something is, but is it? Yeah, it's settling down, all right? And then you can see that in a couple different ways. You could, if you wanted to, plug in this function into your calculator. Let me just do that here real quick. Let's do a fraction here. I want 3 plus 7n squared over n plus 2n squared. And then I can just test it for a few different numbers. So let me go to my table function once I put that in. So second, and then the graph key. I don't want itty-bitty values here. I want larger and larger values. And I guess I'm seeing a little problem here. It's just giving me fractions. I don't want fractions anymore for this one. I want decimals. So there's a workaround for this. Let me go back to the y equals key. And to the right of my fraction, I'm going to ask my graphic calculator to turn these into decimals. So to do that, hit the math key. The second option there says, you know what, just give me a decimal. I don't want these fractions. Second, and then the graph key. That's looking better. So now I'm getting decimal values, but these are kind of small values for n. Let's go n equal 10 or 50 or 100 or 1,000 or 10,000. Did I crash my program here? Let me try that one. 10,000. There we go. It took a while. And 100,000. You can put in as big a number as you'd like. And I wonder why it's taking so long to do that. It's taking a while. It's going to take a little while. But take a look at the numbers that we're getting in the y coordinates. Do these seem like they're getting closer and closer to something? What are they getting closer to? 3.5. So essentially what we're doing when we're trying to find this, all right, and we'll check back on you. Keep thinking about it. You'll get there. I think I can. I think I can. Essentially what you're doing is you're taking a look at the limit as n approaches infinity of your a sub n, or the limit as n approaches infinity of 3 plus 7n squared over n plus 2n squared. You've got a couple nice ways you can calculate that limit. What are those nice ways? Yeah, the exponents have the same degree, right? The degree in the numerator and the degree in the denominator are the same. So this limit is 7 over 2, which is 3/2. Nice. So equals 7 over 2. It comes just directly from that. Now that's one way you can do it. What's another way I could calculate that limit that's very relevant and appropriate to our course? L'Hopital's rule. Yeah, well done. You can do it with L'Hopital's rule. Or you could multiply everything here by 1 divided by n squared. So if you wanted to, you could rewrite this. That'd be the same thing as the limit as n approaches infinity of 3 over n squared plus 7 over n squared plus 2. So you're just dividing everything through by n squared. Excuse me. And now you can take the limit of each of these kind of individually. What happens to the limit as n approaches infinity of 3 over n squared? Goodness. What do I get? Just this little piece right here. Yeah, it's going to be 0. As n approaches infinity here, well, that's just still 7, right? Because this is independent of n. This is 1 over n. And as n approaches infinity there, you're going to get 0 plus 2. So this way, L'Hopital's rule, or the best thing, I guess, would be leading coefficients. Don't forget about that one as you're working through these things. You're not going to get extra points by working extra hard. So try and make it as easy on yourself as possible. Let's take a look at the next one, unless there's some more comment on this one.
I just wanted to know.
Yes.
Limit as n approaches n. Is that what that says, and what does that mean?
N approaches infinity. Oh, that should be...
Okay, cool. Thank you.
Thank you. All right. Let's move on down to the next one. We'll call this example Q to just kind of keep these distinguished. So this time a sub n is n to the 4th over n cubed minus 3n. We're going to look at the limit as n approaches infinity of n to the 4th over n cubed minus 3n. And you're going to kind of run into a problem with this one. Let's take a look at it on a graph first. And take a look at this. It finally figured out n equal 100,000. I knew it would catch up. I knew I had faith in you. So let's shut this one off. You can kind of see here that y equals 3.5 is your horizontal asymptote. It gets closer and closer to that. It'll never quite touch it. But let's take a look at this function, and let me get back to here. Does this graph here look like it's settling down? No. That's as x approaches infinity, this graph is going to approach infinity. In fact, you could play around and probably find an asymptote for that graph. That's not something I'm really worried about here. But the problem is the degree in the numerator is greater than the degree in the denominator. So that limit's going to go to infinity every time when that's happening with your polynomial terms. So if that limit is infinity, then essentially you're saying that this sequence diverges. It does not converge to anything. Whereas in the previous one, up here, the sequence converged. Let's keep on going with example R. In this case, R is going to be e to the negative 2 over square root of n. It might be helpful to rewrite this as 1 over e to the 2 over square root of n. Nothing wrong with that. Just getting rid of that negative in the exponent. If we take a look at the limit as n approaches infinity of 1 over e to the 2 over square root of n, well, the numerator is going to stay 1. Let's take the limit of the denominator. E is going to stay the same. So what we need to focus in on is what's going to happen to this exponent as n approaches infinity, 2 over the square root of n. Cameron?
It turns into 0.
Yeah, you're heading towards 0. So let's see, that's going to be e to the 0 power here. What's something to the 0 power equal? 1. Now, how could I confirm that somewhere else? I mean, it looks like it's converging. It looks like I have a limit of 1. So converges. But what else can I do to double check that? If I really cared about, oh, I got to make sure I get this right, what can I do to double check that? Yeah, you can look at the graph. Nothing wrong with looking at the graph. You should see that same thing. So let me kind of zoom in on the x-axis a little bit. This increases for a while, but it doesn't do so forever. I mean, well, I guess it does technically, but it slows down. Let's put in the line y equals 1 in here. And that graph there is serving kind of like a ceiling to this function. It's going to get close to, but never quite touch, that dotted horizontal line of y equal 1. Y equal 1 is your limit. You could also check that with some numbers if you put this into your graphing calculator. All right, one last one. And it's kind of a cute one. It's got a nice little point to it that I want to share with you. So we'll call this example S then, just kind of sticking with the notation. We've got a sub n equals ln of n plus 2 minus ln of n. Now this one does something kind of unusual and or funny. You know, I think if we were summing up terms in a series that you would see this better. But this is a sequence, so darn it, kind of bummer. I want to take a look at the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of the ln of n plus 2 minus ln of n. And if you're looking at this going, well, that kind of feels like infinity minus infinity. And you're like, well, infinity minus infinity is 0? No, we can't really say that. Can't be quite that loose with our use of infinity. But there is something we can do here that will make that a little bit clearer. Let's take a look at the graph real quick and see if the graph can offer some insight as to what to expect. So here's a graph of ln of x plus 2 minus ln of x. Where does that graph look like it's headed? Yeah, I mean, no matter how much I zoom in, that graph looks like it's determined to get to the x-axis, that it's determined to get a limit of 0. And I can't emphasize this enough. The answers you should get here should match what you see on the graph and should match what you see when you're putting in numbers, if you're just doing this on a table. So if you're getting different information from those different three things, something's wrong. Probably the stuff that you're doing here. graphing calculators, as long as you're putting things in correctly, should be giving you good information. Let me give you a reminder here. Reminder. Log of A times B is a log of A plus a log of B. Another reminder of the same spirit. Log of A over B. What's that one equal to? Log of A minus log of B. And not that we need it, but for sake of completeness, log of A to the R power. That R comes out in front. R log of A. So those are some reminders. Why do you suppose I gave that reminder to you here?
Because we're subtracting.
Yeah, you're subtracting. So what you want to do is you want to rewrite it. So you're going to rewrite the difference of the logs as the log of the quotient. So that's going to be the limit as n approaches infinity of what? What am I going to take that limit of?
ln of n plus 2 of n.
Yeah. ln of n plus 2 over n. And the nice thing is that because this is a nice continuous function, I can reorder these terms. I can take the limit inside, take the log of the limit as n approaches infinity of n plus 1 over n. Can someone tell me what that limit is? Cameron?
Should it be E?
No. It's a good question. It's not E.
Infinity over infinity?
Infinity over infinity doesn't exactly work there, but there's a couple things we can do to figure out this limit. Things that we've done before in this class. In fact, things that we've done today.
Coefficients.
Why can I look at the coefficients?
Powers of n are the same.
Yeah, well done. Thank you. So this is n to the first power, this is n to the first power. If you've got a rational polynomial and the exponents are equal, then it's just going to be the ratio of the leading coefficients is going to be your limit. So what's that limit turn into? Yeah, you're going to get 1 over 1, which is just 1. I'll write 1 over 1 in case you're looking at these notes later and wondering, well, where did he get that? It's just the ratio of those two leading coefficients. Help me out here. What's the log of 1? 0. Just like the graph says. Yes, sir.
Why did it change from n of n plus 2
Oh.
to n plus 1?
Must have been a little dust on the lens. It didn't really change there. Yeah, no thanks. Thank you. All right. Whew. Went through a lot there. We're looking okay with limits and converges or diverges. This one converges. Nice. Wow, that's going to be a long video. I pity anyone who's still watching this one.